Now this question says determine I/O in this circuit. So where is I/O in this particular circuit? Well, we know I/O is going to be the current flowing through this 4K resistor. So it's going to be in this branch here. Now, they want us to find I/O in this circuit. How do you think we should go about this, right? We have a voltage source here. And because this is the only voltage source, we can assume that the current is going to flow in this direction here, right? We can make an assumption that current is coming in this direction here. And once it enters this node right here, it's going to split. Some of the current is going to go this way, and some of the current is going to go this way. So even though they drew the current coming into this node, right, that drawing might be wrong. It might actually be leaving this node, or our assumption might be wrong. We don't really know. The only way we'll know for sure is if we find the current I/O, and if this current is negative, then we know the current is actually flowing in the opposite direction. So let's continue, right? So we know this current, let's just label this I/O. No, we're going to label this current IS, right? So we have IS, we have I/O, right, which is this current here. We're going to assume that it's actually going to come into the node, and we have this current I1. Now, as I1 reaches this point right here, we know I1 is going to split. I1 is going to go this way, so we're going to call this I2, and it's going to go this way. We're going to call this I3. So when we look at this now, we can see that these two resistors are going to be in series, right? So we can actually redraw this to be, we know this is the 4K resistor, this is the 2K resistor, this is 12 volts, this is the 4K resistor, this is going to be 16K, and we're just going to add 4 plus 12, right? 4 plus 12 is going to give us 16K ohm. Now we can continue to reduce this. We know these two resistors are actually going to be in parallel. So when we find the parallel equivalent for these two resistors, we can say 16 times 16 over 32, and that's going to give us 8 kilo ohm. So let's now redraw this circuit, and when we redraw this circuit, it's going to look like this. We're going to have 8 kilo ohm. This is going to be a 4K resistor. Then we're going to have a 2K here with a voltage source. And we have this resistor here. When we look at this, we have 2K, we have 4K, and we have 12 volts. Now we can continue to simplify this. We know these two resistors are actually going to be in series, right? So because these two resistors are in series, we can now simplify this to look like this. And we know we got 12K because we're going to say 8 plus 4 is going to give us 12 kilo ohm, which is going to be this resistor right here. So we have 12 kilo ohm. We have a 2K resistor here, 12 volt battery. The signs are a little different. It's going to be negative, plus, and we have a 4K resistor right here, right? Now when we look at this, we know they want us to find the current I/O, right, which is going to be in this branch here. Now I want us to notice something, that these resistors are all in parallel, right? So because all three of these branches are actually going to be in parallel, we can redraw this, right? Because this circuit is the same thing as this circuit. Do you see that? They're the exact same thing. So because they're the same thing, we actually can do something with this now. We can say, okay, since we know these resistors are in series, we can actually combine these two resistors by taking the parallel combination of it. So we can say 12 times 4 over 12 plus 4. That's going to give us 3 kilo ohm. So we just combined these two resistors that are in parallel, right? Which is really just these two. So if you don't know, you can actually redraw this, right? Let me just redraw it for you. We could have redrawn this to look like this. We could have said this is where the 12K resistor is. Then we're going to move the 4K over to this side as well. We can say, okay, this is the 4K. And we're going to have this branch right here. That's going to have a 2K resistor and the voltage source. So we just redrew this circuit to look like this, right? Same concept, because these resistors are all still in parallel. Now, once we found the parallel resistance of this, we actually got 3K. So I'm just going to redraw it once again. So we have 3K. And we have a 2K on this side with a 12 volt source. This is 2 kilo ohm. And this is going to be 3 kilo ohm. And we found that when we combine these two resistors that are in parallel. Now remember, the current they want us to find is I0, which is through the 4 kilo ohm resistor for this leg, for this branch. So all along, we know that IO was here. So this was IO, right? We know this was IO. This was IO. And we know this branch right here was also where IO was, right? That's the current flowing through this 4K resistor. Now, once we combined these two, using the parallel combination for resistors, we no longer have IO, right? IO has now disappeared. But what we do have is this new resistor, and this 3K resistor is actually going to be in series with this 2K resistor. So now what we can find is going to be the current source, which we labeled here as IS. So even though we had IO, we also had IS the entire time. So this was IS, which is the current source. This was IS. This was IS. This was IS. And once again, we have IS, which is going to go this way. So now when we solve for this, we can use Ohm's law to find IS. We can say IS equals V over R. We know the voltage is going to be 12 over, and we have 3K plus 2K, which is going to give us 5K, and 5K is just 5,000. So now we have 12 divided by 5,000. When you put that in your calculator, you're going to get IS equals 2.4 milliamp. Now this isn't our answer. They want us to find the current I0. Now, even though this isn't the current I0, this might help us to find the current I0, right? So we know I0 is going to be going through the 4K resistor here. Okay, now that I have this, there are multiple ways we can proceed. Now, the way I'm going to go about this is because I have two resistors in series, right? And we know the voltage in that loop. I'm just going to find the voltage across each resistor using voltage division, right? So I'm going to say the voltage across this 3K, I'm going to label it as plus, minus. I'm going to label it as V1, and I'm going to label this one plus to minus. I'm going to label it V2, right? because I imagine the currents coming in to the resistor at the positive terminal. That's why I label it plus the minus, right? All passive sign convention. So sometimes you have to label these things and just assume, but you have to be very comfortable with being intuitive in understanding what's happening with each circuit. We know the current wants to enter the positive terminal. That's why I have it as a voltage drop. All right, so now to find the voltage V1, we're just going to use voltage division. We're going to say V1 equals Vs multiplied by R1 over R1 plus R2. Now when we start to simplify this, we know the voltage source in this particular situation is going to be 12 volts. We have V1 equals 12. R1 is going to be this 3K, so we have 3,000 over, we have 3,000 plus 2,000. When you start to solve for this now, V1 is going to equal 7.2 volts. So if V1 is 7.2 volts, we know V2 is just going to be Vs minus V1, which is 12, minus 7.2. Therefore, V2 equals 4.8 volts. Now, is this our answer? No. Does this help us? Maybe, right? We don't really know. Sometimes we just have to go and find things and then just see what we can do from there, right? Okay, so we know the voltage across this resistor and the voltage across this resistor. Now we know this 3K ohm resistor came about because we had two resistors in parallel. And we know anytime we have resistors in parallel, they're going to have the same voltage, which means that these two resistors are going to share the voltage V1, right? And we know the value of V1 is going to be 7.2 volts. So to find the current I0, we can just use Ohm's law. We can say I0 equals V over R. We know the voltage is going to be V1 over 4,000 ohms. Now when we look at this, we know I0 is going to equal V1, which is 7.2 volts, over 4,000. But I want us to notice something, right? This current is actually coming through the negative terminal, which means this is going to be a negative current when we solve for our answer, right? So when we solve for this, we're going to get I0 equals negative 1.8 milliamps. So this is going to be our answer for this particular problem. I0 equals negative 1.8 milliamps. And we know why it's a negative current, because the current is entering the negative terminal here. So you can treat it as a negative voltage if you wanted to, but I like to always treat it as a negative current. So it's important we understand what's happening here, right? This problem wasn't too difficult, but there was definitely some steps involved, and we had to be able to understand exactly what happened. So let's go over this one more time. We know we had a source current leaving this positive terminal here, right? It's going to come in this node and it's going to split. It can go either this way or this way, right? Now, when we look at this, we know these two resistors are in series. We combine these two resistors. 4 plus 12 gave us 16. We just redrew the rest of the circuit the way it was, right? Now, when we look at these two resistors, we know these two resistors were in parallel. So we perform parallel resistor combination for these two resistors. We got 8. So we wrote back 8 and we redrew it right here. Now we redrew back our circuit the way it was. We know these two resistors were in series, so we combine these two resistors. We got 12. That's how we got this 12 here. Now we know that all three of these resistors, or you can say all three of these branches, are actually in parallel. So we can redraw it to look like this, right? With it actually being vertical instead of horizontal, right? Sometimes that's easier on the eye. Now we can actually move this around. So instead of it being a resistor and the source and another resistor, we actually just move the two resistors side by side, right? Just like this. We perform parallel resistor combination on this. When we did that, we got 3 kilo ohm. So we redrew the circuit one final time, and we had a 3K resistor with a 2K resistor. Now we were able to perform Ohm's law on this. So we found the current IS to be 2.4 milliamps. Once we got 2.4 milliamps, we were then able to say, well, maybe this can help us, maybe it can't. For this particular situation, we didn't even use this current, right? Because once we looked at this, we also knew the total voltage for this particular circuit. We knew that was going to be 12 volts. So I decided to just perform voltage division, just for practice, and we were able to find the voltage across this 3K resistor and then the 2K resistor. But we noticed something. We know this 3K resistor was made up of two resistors that were in parallel, which was this 12K and this 4K. We know resistors in parallel are going to have the same voltage. So once we have the voltage across this 3K, essentially we knew the voltage across this 12K and this 4K. Because we knew the voltage across this 4K, all we did is we performed Ohm's law to find I0. So I0 equals V1 over 4,000. Once you calculated this, you got negative 1.8 milliamps, and we knew it's going to be a negative current because the current is going to be coming down this resistor, right? But according to our polarities, the way we drew it, it's going to be a voltage rise from negative to positive, which means this current enters the negative terminal. So therefore, we're going to say it is a negative current. So this is how we were able to solve this problem. This one was a little more challenging than the ones we saw before, but it's not too much more challenging. All of these are just tools we need to have in our toolbox and be able to pull them out when needed.